Hello all, welcome to the Compute Memory and Storage Summit. My name's Andy Banta and I'm here to talk to you about optimizing complex memory and storage systems. I'm doing this work on behalf of Magnition IO. A little bit about me, I've been in the high-tech industry for over 30 years and most of this time has been spent in storage and compute type industry. If you have any occasion to contact me, you can do that at my addresses listed in the last line here at Andy Banta on Twitter, andybanta.com at Magnition.io, or you can check out my webpage at andybanta.substack.com. I'm here to talk to you about some of the challenges involved in building complex storage systems or content delivery systems. In this day and age, we end up with multiple layers of various different storage and memory devices cascading into each other, and there's many different interfaces, many complex interfaces between these, including caching and memory systems that need to be used in their places. There's all sorts of issues this brings up: how to handle latency, how to size your caches, how to know what workloads you're working with, how to handle all the latency associated with various service level agreements. And one of the real problems with this is as the number of layers increases, the complexity increases not linearly, but exponentially with the number of layers. And it becomes such an issue that you can't actually have somebody sit down and draw out on a piece of paper how they're actually going to build a complex storage system or content delivery system. You can't even have a team sit down and kind of design this. You actually need to have some way of automating the process of figuring out how these various different components fit together. That's where Magnition comes in. Magnition has actually worked on this problem already, figuring out how to handle data placement, figuring out how to cache sizes, figuring out how to build large-scale storage systems and content delivery systems. The content that's been provided by Magnition includes multiple patents, multiple papers on the research involved, and proven customer track records. So we have to actually take a slightly different approach to optimization. The idea we have here is that we actually are going to simulate the complex system and figure out how to optimize it that way. So we typically will break the simulation down into a lot of different pieces, the various different components that you might have in your system, storage boxes, memory systems, compute system, caching, whatever. And then we allow you to build these various different components into a complete system just any way that you want. When you're doing this, you can actually provide a number of variables in any one of the components or multiple components that you can test and try to figure out what is the best way to optimize your system. And you can run these systems against synthetic data, or you can actually run them against real I/O traces. Magnition has a library of real I/O traces, or you can capture your own real I/O traces and run them against your simulations to figure out what's best for you. The value of simulations is that they are very easy to put together. You can build them much faster than you can actually build physical compute systems. The only compute system you really need is a computer to run your simulation on. That means that you don't actually need to go buy hardware for all of this. You don't need to buy various different types of memory. You don't need to buy various different types of SSD. You can actually simulate them all. It also means that you can actually try all these different things and come up with various different ways of optimizing them. You can simulate all sorts of different variables and come up with what is the best answer for you. If you think about it, when we actually build hardware systems these days, when we actually build chips, we run an assload of simulations on these, and they run simulations for days to optimize the way that the chips are laid out, to optimize the power consumption of the chips, to optimize the performance of the chips. If we did the exact same thing in system design and software systems, we could actually optimize those much the same way. So the end result is that you end up with lower cost, you end up with higher speed to actually get to your results, and you end up with far more flexibility than you would if you were actually trying to build these systems on your own. How do we do this? We actually work from a library of components that are ready to use. The Magnition has this library of components, and they fit together in a software simulation framework. The nice thing about this is that if you're actually a company who's developing new products, you can actually have your developers build their own components that fit into this framework, and it can be a mix of libraries of components from Magnition and things that your developers have actually built. So the basic building blocks we have are caches. And the idea with the cache is that you have an input and you have a hit direction out of it and you have a misdirection out of it. So the idea here is that this is one of your decision points when you're actually building frameworks. And the caches are going to be talking to media components. So a media component could be memory, could be disk, could be cloud storage, could be any one of these other things. So you have a hit type media and you have a miss type media. The pieces that actually string these together would be, we call wires. They're just connectors. They're various different ways that information gets from one place to another. So the wires, in this case, we actually can build it out to a multi-layer cache. So in this case, you can see we have an L1 level cache and L2 level cache, and you can build these out any way you want. The caches could be in parallel. You could have multiple caches that way. You can have all sorts of different wires as well. So let's look at what's actually inside a cache. We actually allow you to choose a handful of different fundamental algorithms to fit into your cache. Things like lookups, allocation, eviction. So like your allocation could be a slab allocator or, just whatever allocation methods you want. Your eviction methods could be LRU or FIFO or whatever, and those all dictate how your lookup works. You can actually have more than one hit direction out of it. So say your cache actually works on a pool of SSD drives. You might actually want to know which SSD drive you're actually putting the cached information into. And your misdirection could actually have a variety of different directions as well. You could actually be drawing things from more than one origin. So you would actually have the cache figure out which origin you want to go to. So let's actually talk about the media component a little bit more. The media component is memory, disk, cloud storage, flash, PMEM, whatever you want. Magnition has a handful of pre-built simulations already. One of the most interesting ones is one called MQSim, which is a SSD simulator. The things that the media components have to simulate are things like parallel access. So it's not just like memory would have a few nanosecond delay. It's if you actually have contention, if you have queuing for like a disk where you have multiple requests going in, not only is the disk going to hold off requests at some point, but the more requests a disk is handling at any given point, the slower all of those requests are going to go. And you have to think about things like, if you're just thinking about things like memory, is it DRAM that's going to have like a couple nanoseconds delay, or is it going to be something like PMM that might have tens of nanoseconds of delay? These are things that you actually have to figure in here as well. The cool thing about simulations is you don't actually have to deliver any of the data. All you have to do is simulate the delay that's associated with it. So in our multi-level cache here, we can say that our first level cache is DRAM, and we throw in SSD as our second level cache. And then off on the far end, we actually have something like network storage. So a storage array, something like that. It could be cloud storage. It could be anything. Now let's chat about the wire component. So the wire components, much like the media components, are going to be things like memory buses, disk controllers, networks. Keep in mind that a wire component can multiplex. That means that you can actually have like one input and multiple outputs on it. A wire component could also be like a disk controller, where it's going to take a big memory chunk and it's going to change that into a bunch of different disk I/O commands. So just think of the wire as something that transports the data, but it could actually multiplex it, chunk it up, reconstitute it, a variety of different things that wire can do. It's just one of the things that goes between your caches and your media. Keep in mind that even the type of wire can have a variable delay. So in this case, like say we have something that comes in on the URL request, the first level cache. If the first level cache has a RAM bus connected to the DRAM, it's going to be a certain amount of delay. But conversely, if it's like a CXL connection to the DRAM, you're then going to end up with a different type of delay. Keep in mind again that delays are going to be introduced by contention and queuing on the wires as well. So in between these multiple caches, we would have a PCI bus. Our second level cache might have like an NVMe interface to the SSD. You could also have like a SATA interface to the SSD. One of the cool things about MQSIM that I mentioned in the previous slide is that it actually provides simulation for either a SATA interface or an NVMe interface. And finally, we'd have something like iSCSI that would go off to our network storage. So at this point, I'm going to actually break out of this and show you how we actually simulate this in our actual software framework. So in this case, we actually have the framework laid out, and we can actually see here that we have like a couple different servers that are serving the request. So if we take a look inside server 1, you can actually see that there's a couple caches here. There's a L1 cache and an L2 cache. And if we take a look at the L1 cache, we can actually see that it's connected up to DRAM, as we talked about. And if we actually take a look at the cache algorithm itself, you can actually see that there's a couple different components of that, like the allocation, lookup, and eviction methods that I had talked about. So what does this mean to us? This actually means that we actually can get some real performance results. Here is a graph that actually shows some of the results that we would get. In this case, you can actually see that by changing the size of the cache, we end up with various different knees in the line. So we get an idea of where we actually get some good hit performance ratio. And then at the final knee, we can actually see where we've gotten the entire working set in cache. So we're not actually we don't actually have any misses. Depending on the expense of your cache, you might actually want to be somewhere in that middle area with the idea that you actually are going to have some miss ratios as well. We actually have worked with a company, one of the companies that's actually participating in the symposium this week, worked with Magnition over a handful of months to actually provide, come up with much better performance for their system. They actually demonstrated some pretty significant performance results, and it's actually integrated into a product that is shipping today. So here's a little bit more information about that. You can actually see that when without Magnition, they were only able to run a couple experiments a day. With Magnition, they were running thousands of experiments a day, and the number of experiments that they had run before they actually started working with Magnition was only 50. After Magnition, they'd done over 1 million various different simulations. So there actually are real results, and here you can see that that they actually optimize their output by 10 to 50% depending on the workloads. That brings us back to what Magnition can do for you. So Magnition can actually go through and help you figure out how to optimize your system, figure out how to handle the cache latencies and data placement. We've actually been proven, this has been proven. We actually have working customers who are out there doing that. And we have loads of publications out there that you can actually look at and review yourself. We don't actually try to hide anything. Everything that we work on is out there for you to see. If you're interested in finding out more about Magnition, tune in about a month or so, and I'll be providing a much longer webinar that goes into a lot more detail on our products. Thank you for your time today. I hope you have a good day.